Now it's my honor to introduce our keynote speaker, Dr. Zhongming Shi. Dr. Shi is the product lead of the City Energy Invest, an open source platform for low carbon urban design, and teaches the Integrate Design Project Studio at ETH Zurich. He completed his PhD at Future Cities Laboratory in Singapore and later coordinated the CP's Knowledge Graph project at Singapore ETH Center. Please join me in welcoming Dr. Zhongming Shi.
Hi everyone, my name is Zhongming. Thanks for the invitation, Jonathan and Marga, for all this work background. It's very interesting that when I was just about to finish my PhD in 2020 to 2019, I just came to Jonathan's work from journal publications, and I realized there's someone doing almost identical work as I've been doing in Munich, which is really nice. And later, 2023, I came here for a holiday, and I reached out, and we had the first ever meetup. It was very, very nice, very fun. And I'm so happy today I got invited again to be here to introduce some of the work that we have been doing related to bringing building scale research into urban quarter scale or district scale research, and also what's currently our pipeline. My topic today is Future Cities Through Science by Design in Place, which is the slogan of FCL Future Cities Laboratory. I found it very much reflecting the philosophy we're trying to work on, like combining science with design and also in place, which is like you have to pay attention to that local context. So first, acknowledgement of my chair, my team. We are the Architecture and Building System Research Group, which is part of the Institute of Technology in Architecture, and which is Department of Architecture in ETH Zurich. And this is the group photo like we took last year, and most of my colleagues are engineers from different perspectives, and you're field designers. Myself is an architecture and urban design background. We have two home bases. One is in Zurich, in Switzerland, and this is our office at ETH. The other one is in Singapore, which is more lushy and high-rise and can really reflect the common typologies of the buildings in the two cities. What do we work on? So this is a building that's looked very lushy and very green, like one of the condominium, many condominiums inside Singapore. And many buildings are trying to be green and large on itself. However, when it works together with the surrounding context, it comes in with the other problems. And we want to study wood, at least wood. Back then, at the beginning of the Future Cities Laboratory second phase, we're trying to decipher the interdependencies of the cluster buildings, let's say 20 to up to 200 around that scale, and how buildings are having synergized collective impacts on environments. So we studied in interplays, like I just mentioned, the design and energy engineering. When we talk about this topic, the first thing come to our mind would be building energy performance. So for these urban quarters, if you dissect it into floor areas and the location of different densities in different, like spatially distributed areas, and also the land uses types, like let it be residential, commercial, retail, or whatever, it comes in these building energy demand, which have also attribute in terms of space and time. So we want to study how we can allocate the use types and the quantitative use types, the ratios of them as mixed use, also that distribution of the density of floor areas around the urban quarter to best impacting on this building energy demand. And just now energy demand, in addition, we want to study the interplays between the design side to the supply side. There's building and there's demand, and then there's the supply. So we want to study all the three parts together, not just simply reducing energy. So we call that the active design measures, especially for the supply system's efficiency, and we also want to make the most use of the on-site renewable energy resources. Hence, we go hand in hand of all three aspects, supply, demand, and design. Now let's see an example. I use a BIPV example, building integrated photovoltaics. When designing a BIPV district, what are the passive and active design measures? For example, like this is a very common metric to measure how well you're doing when doing the BIPV design. It's we call it different ways, but in our GR we call it solar energy penetration, which is a very simple metric using annual PV electricity yield divided by annual energy demand. I mean, there are many other metrics that I'm using this one as an example. So as you can imagine, you want to increase the annual yield and reduce the energy demand, right? It's very simple. Like reduce the energy demand is the passive measures, and improving the PV yield is the active design measures. So when it comes to urban context, things become more complex, and there's neutral shadings. So we want to study, like for example, in the district, what will be the highest achievable solar area, highest achievable solar energy penetration? And when you achieve that solar energy penetration, what would be the design metrics behind? Hence, with these case studies inside Singapore, so this is, if you know the skylines of Singapore, all the beautiful skylines are right here. And inside the city center, there's a terminal section, and where it's going to be repurposed as a future urban district. And we were working on it, like envisioning what would be the potential future urban form of this district. So based on the question we just had, was what could be the highest achievable solar energy penetration? And we did analysis for this particular site, and the highest achievable solar energy penetration, if you look at this axis, and will be around 70%. And if you look at if you can lower your standard, let's say if you only want to reach 30% of solar energy penetration, and you see this chart, you can build as dense as reaching almost 10%. Although as dense as FAR equals to 10. And the color represents the mixes of different use type behind and the ratios. So we studied this site and come up with this diagram to show when the planners need to have a metric for the particular district, and this diagram could be used as a guidance of what could be possible on the site. Like if we look at another number, if the goal is only 10% of solar energy penetration, and you can achieve as high as FAR equals to 15, and then you have more flexibilities on choosing the mixed use ratio. And why it's like that? It's because, I mean, as you can already know, that the UI, the energy use intensity of different uses are very different in terms of the quantity. And also, they have another measure, which is the temporal measure. If you see these charts, for residentials, most of the uses happening during the evening hours. For office and retails, mostly happen during the day, right? And for the PV electricity yield, it comes in another, like, it happens through, like, always just during the day. So here comes discrepancy that the hours of production and consumption are really matching. So that's here we study like how we are going to find the right amount of ratios will match these PV yield, electricity yield, to avoid additional storage. And why we're talking at district level, because at district level, in terms of scales of economies, and there's more flexibilities, you can make combinations of different things to achieve what you want to achieve. And the single buildings will be rather difficult. And the same district and different uses or different buildings, they combine together and with different uses, and you have more flexibility of trying to match the curve of the previous, like the yield and the production. And remember just now I mentioned the active measures of supply, like making the most use of on-site solar renewable energy and improving the supply system like performance. And these charts, if you follow my pointer, so for the whole district, 100% of the time of the year, and the load is about 10K. And then 20% of the time, the load can reach more than like 33K. So you need to design a supply system at this point to meet the highest use of the hours of the year. So the entire dish area is blank and wasted. Imagine you have built a really, really big energy supply system, and you're making it idle for most of the time. That's not very economically making sense or viable. So what we were trying to do is finding an interplay between the design metrics and the performance of the supply system, which is measured by this chart, and try to match that or fill that gap. Anyway, so back to the PV question. The solar energy coming out of the PV panels are not completely clean. I think probably everybody knows that. That's because when you manufacture PV panels, and then there is emissions coming out of it. So there's also a carbon intensity coming from the PV electricity. But just now, like we said, based on the context, the intensity could be have different indicating effects. For example, if we see this chart, I just quickly look at Israeli's city grid, the national electricity grid, was the carbon intensity inside, and compare that to the Singapore one is quite comparable. It's like around 500 grams per kilowatt hour electricity. So this curve represents a common PV panel types, like the carbon intensity behind. How do we use this chart to determine where on the building facade is eligible for PV panels in order to have the PV electricity yield coming out of the PV panels have lower carbon intensity compared to those ones coming from the city electricity grid? As in Switzerland, the same number is 50 grams. So meaning that on building surfaces where we receive more than 800 kilowatt hour solar radiation per year can finally make the electricity coming out of the PV panels like comparable to city grid. Like I give you some example to make you understand this metric. So when you want to max out the yield of building on PV yield, you would just put PV panels everywhere, right? And this is not viable and it's not economically making sense. So when you only select the area, we have like a threshold 200, and you see some spaces got left out. And for example, in Singapore, it's more like 200 is the threshold. You know that if you place PV panels on these colored areas, you will have emissions like lower than the electricity coming from the city grid. But however, in Switzerland, the exact same building, if we place it in Switzerland, only these areas are viable to place PV panels if you want to make the electricity cleaner, coming out of the PV panel cleaner than the electricity coming out of the city grid. And how do we use it? So you can zone the building and a different threshold. And then, as you know, there are all types of PV panels. They all comes in with different efficiencies and different price. And then as an architect, if you study back from the urban scale or the core district scale to the building scale, and there comes in the time that you can decide what type of PV is more suitable for these zone buildings. And as a facade design, and you can also come in with these PV type ideas, and then also matching the indoor layout design to the outdoor BIPV design. So at this just end of the example I gave for the DIPV design, and a quick summary about our work model is from urban and architectural design to building energy demand. There's cooling, heating, whatever demand. And then you need to design a supply system to match that demand. And then all these comes in with emissions, let it be operational emissions and volume emissions. And the way you design the city or the way you design a building, based on the material used for the construction, and it also comes in with emissions. So all these four parts are interconnected. And then there's also additional metrics, including costs and environmental impact. For example, in Singapore, there's a lot of anthropogenic heat ejected to the surrounding ambience from the cooling heat system, and we don't want to cause urban heat island effects. And then also usability. So all these metrics combined together, and we want to study, or we wanted to study the interdependencies between all the way to the left, urban and architectural design, to the metrics on the right. And here, this part is more energy engineering modeling side, which is through science, and the other side is the design. And I want to acknowledge the title I have is by design through science in place, as this is to be happening in different, very vastly different places. The next part, I will briefly mention about the methodology we have in the chair, not just our model, not just my project, the entire chair, which they're relevant to what we have been doing. First one, we use data. We use Google Maps data, which, as if you remember just now, we talked about the energy use intensity and also the energy use curve. And where does those curves come from? And they come from most likely energy simulation standards, which could be produced long time ago, like in the 70s. And when in reality, it's very context specific. It's different from Haifa to Tel Aviv. It's different from Singapore to Zurich. But most of the time, we're using the same curve everywhere. And how where we can update the curve, and we come up with this Google Map method. That's if you check Google Maps, many of the times you see the popular times, and that's exactly when it can be used as a proxy of how energy is being used. And here is an example of a CTA based on Google published times. The city is orange one, and the blue one is another city. And both of these cities are from the US, actually. And so the gray area is the occupancy standard for energy modeling. So you can see how different, even within the country that is where the energy occupancy standard modeling is produced is very different. And it has all these will impact our energy modeling. And we also use the data because we always say we want mixed use. Like how mixed is mixed use? We want to understand the DNA between the mixed use kind, especially when we want to model, for example, a mall, you cannot simply say it's a commercial because it's a combination of supermarkets and restaurants and stores, retails, and many, many things. And we like to understand what's really behind it at a more granular level. And here comes in Google Maps data again. That's as each business is labeled with one of these guys throughout the world. And we can use the data we get from Google Maps and combine it with some machine learning techniques, and we come up with this DNA, say, of a mixed use plot, which can make our modeling more granular. And overall, we combine empirical experiments and computational simulations. Just now, I give you some examples of computational simulations. And as you can imagine, some of the times you need to gather the data based on actual empirical experiments. And these two are helping on each other. It's a synergy. For example, how we gather the empirical experiments data. This is the one project we did in Singapore that we want to study how vegetables are being grown on the building facade. And we can use our models to scale up in the district scale, but we need the yield data, how much actual yield you can generate from the building facade. And then that's why we collaborate with the National University of Singapore, who has this lab, so we can actually acquire the data of the yields of vegetables, and then use our model scale it up to an urban scale modeling. Another example is in a chair. This is ETH again. You see our buildings behind, and there's a small building in front of it, and it's zero carbon building system lab, which is artificial sunlight, artificial solar simulation. So imagine if you produce or you printed or a new building facade material, you want to study the thermal attributes of the material, and this lab can produce or generate like a winter environment, summer environments with the sunlight, and you can use this way to study the thermal attributes, and then which can be later fed into the computational model. And within the chair, there are building skilled people and urban skilled people. I'm the urban skilled people, and then there's also a building skill tool, which is a Grasshopper plugin called Hive, which can also take a look if you're interested. I mean, the tool does building level energy simulations. How much time do I have? Okay, still have time. Okay, so back to the work I'm doing. So far, I finished talking about overall the research in the chair and how it's relevant to us. And then this is the project I've been working on. I'm leading this project called City Energy Analyst, which is a product has been around since 2013, and it started with one PhD thesis. And I was the second generation who worked on this software. And then later I left and I returned. So currently right now I'm leading the tool, but it's a group work. And it's a district level simulation. I'm not sure if you have heard of it before. And we had a definition of the tool. And CEA, short name, CEA. CEA is an urban building energy simulation platform, and is one of the first open source initiatives of computational tools for the design of low carbon and highly efficient cities. And CEA combines the knowledge of urban design and energy system engineering in an integrated system platform. And this allows the study of the trade-offs, effects, the synergies, and the interdependencies between urban design scenarios and energy infrastructure plans. And we, as the CEA team, is committed to empowering researchers and practitioners to plan and design low carbon cities. And so following this concept, I'm briefly showing the workflow, which I just introduced. With CEA, we generate the energy demand results, which is the energy demand forecast. And based on that, CEA can auto design the supply system and optimization. And as we try to make this model very easy, we minimize the input requirements to more or less like that, like building volumes, how many floors, and what will be use types. And with these inputs, can quickly generate, very fastly generate demand results and supply or design of the supply system. Hence, this supports our study. And I mentioned in the beginning, we want to study the interdependencies between active and passive measures of urban quarters. I give you some example. This is one of the use case. It's about emissions. So usually when you have a software and you want to study the emissions, and we can generate the data. We know building A is 55 tons emissions per year. And building C is 51 tons of emissions per year. And this is not really helpful for designers. And what we want to achieve is, for example, in the retrofitting scenario or urban regeneration scenario, which building has more potential to be retrofitted first? Which building should be wrecked later? And which building should be just demolished and no use, no values, and should rebuild? And which building should keep as is? Especially when you have limited funds. It's not always the case, you can just retrofit everything. And that's a perfect career scenario, right? So we want to achieve these. So currently CEA has a method to do so, and we're working on to automate this process. Another example, back to the DIPD example, instead of just trying to know what will be the potential for each buildings, we want to know, like, achieve the facade design part, like where on the building facade is suitable to place what type of PV. This is something we are trying to automate currently. And some story behind, like, through 3 weeks ago, we just released a new version of CA, and we named it CA4 in Shanghai Climate Week. And I also had a chance to be featured as a product from Switzerland in the 2025 Osaka World Expo. So CA4, now you can use it almost anywhere. That's for designers, including Windows for Apple system as a desktop. And then there's also the online version now. You can use CA online. Later I will share a link if you want to play around. Then we also reintroduced Grasshopper plugin, which is our users keep like trying to make us produce this Grasshopper plugin, and finally made it. The story behind it is when I was doing my PhD, and they made this plugin for me only. And after I finished my PhD, and no one maintained it, so we never had it again. And only this year again that we reintroduced our plugin interface, Grasshopper interface. And as the research tool, and we also have the capacity to expand it to link with other research tools. For example, Maxim, LP for energy hub modeling, and or EpiMap. And CA also had the potential to produce its own plugins to use CA features to expand it to solve like more problems. Like just now, the building agriculture problem, we also developed a plugin for it, and you can take a look at our website. You can try it out. As for some impacts, just now we say from research to teaching and to practice, we have a teaching dimension. CA3, the one before CA4, and was introduced in 2020. And we know we have users from 70 plus countries and the world's top architecture programs for teaching. And we know there's few that's using CA for teaching, that it be for studio design or lecture-based course. And we also, in the past 2 years, we start to realize there are users from design firms starting down with CA. So today I'm really happy to see Jacob from Penny Larson, and I know the users downloading CA, but I don't know what they're doing with it. Good time to know. And as we're teaching, I want to show a few slides for how we are using CA for teaching. As we have this program combining architects, urban designers with energy engineers, your top designers, top engineers, and we want to do an integrated design project together. I'm running out of time, so I'm just quickly going through it. So the students basically prepare the data to feed into CA. The study was the common building topologies in Zurich, and they model their site, their district in different climates, the climates of now and climates in the future, and then study the demand scenarios, like what will be the demand in different cases, and then the same curve, which is I just showed earlier, will be the most suitable threshold for PV integration in Zurich in terms of different ways of measuring the solar integration. Just now introduced solar energy penetration. There are other ways to measure too. So they come up with threshold charts to determine where to place the PV panels. And students also study the solar potentials, demand potentials based on the data preparation. And this is like overall looking of the board submission of one team. And 2020, it was 2024 actually. And we did a studio again in Shanghai, which is regeneration to the former World Expo site. And same study has been done. And in a different context, we see a lot of different results, which are very interesting compared to the one we did in Zurich. And interesting enough, like we upgraded CA3 to CA4 together with our students. And we tried to use a production mindset that consider our students as our clients. We gathered the first-hand feedbacks from our students, and then we managed to bring CA3, which looked like that, and into CA4, which is currently what you're seeing. And want to try it and secure code. I'm not sure you have time to. Okay. Okay, sure. It's currently in its beta phase. So today will be a time that we have the highest amount of volume. It's also a stress test for us. It's not designed for the phone, but you can view a test case that on the phone. But if you have a chance, you're interested, please use computer at the same URL to find it. Should I move on the slide? Okay, so this year we secured some funds for a joint studio with Zhongming University in Shanghai. Again, we're doing a studio with China. Personally, I'm very happy to see this because before COVID is a quite common thing for design studios to happen internationally. And after COVID, it seems it's no longer a thing anymore. And finally, this year, we are very lucky to secure some funds and support exchange between students in Zhongming and to come to Zurich, and our students go to China. And probably in the future, we have some funds in Israel do the same thing. And we have this AI-powered CEA, which is in the making. And this year, as we are using our students again as our clients, we hope we can use this chance to apply the AI-powered CEA and polish over this design studio. And I'm reaching the very last slide of my presentation. Thank you for your attention.
Thank you, Dr. Shi. It was an enlightening presentation, starting from what are the strategies, from conservation strategies to renewable energy integration to cut down the energy demand, and also about the CEA, which is your next generation simulation tool. I think this covers the whole of how energy demand can be reduced. Thank you so much. We'll now go for question and answer. Online attendees can please put your questions. On behalf of you, we'll be asking Dr. Shi, and anyone from the in-person attendees can have their questions. Yeah.
Yeah, I wanted to ask if currently the model behind the simulation is based on engineering and physics
Physics-based model.
Physics, and now you want to incorporate, how do you intend to incorporate machine learning?
Okay, the AI-powered, in Shanghai Climate Week, in Tokyo, in Osaka, we managed to speak with many of the potential clients. And we figured it's not possible to entirely just have a CA GPT or something chat. But what we were doing is we're trying to make the onboarding easy. For example, like when you have to prepare the data to feed in the CA model, and right now there's a gap between like how you can prepare this very rigorously restricted format, and we want to make that part easy, which we call data preparation. And also for the simulation part, currently you have to go through like a workflow. You have to study the workflow, and we want to use AI to automate this workflow. So this is two things we're currently working on. Nothing too super fancy, but that I think what we're trying to do is just reduce the amount of variability to get things running. And for usually another use case could be using a surrogate model to make the simulation faster. And that's not something we're doing right now because the simulation is already quite fast. Minutes away, you can get some optimization results of the supply system design. Thanks for the question.
Thank you very much for the lecture. I actually have a similar question regarding the exact simulations which you used. For example, in the picture, we saw panel distribution to balance demand and consumption. Like which algorithm did you use for getting these pictures? Did you have other scenarios of distribution? And like, is it linear calculations or do you use genetic algorithms when you expect them? The
optimization is always genetic, but the demand forecasting we use ESO standard for like the RC model for modeling.
the genetic means that you used something like Wolsey or you use Grasshopper or.
Those ones we don't touch. We become a simulation engine as you as a designer and use our tool like a Ladybug simulation, simulate the results, and you connect it to another Grasshopper native optimization. That's not something we touch. But you can hear that we have two-layer optimization in your problem. Like inside Grasshopper, you want to optimize your urban design. And what we provide is a simulation, like energy performance assessment. And within our energy performance assessment, there's a layer of optimization if you want to. Like that optimization, what it does is a genetic algorithm to determine, for example, which building to connect to district cooling, which building to not to connect to district cooling, and how much PV panels should be integrated in each building. If there's like internal optimization. And that's something only is not exposed to you, but it's inside CEA. But for your optimizing your urban form, that's what as you as a user, and you will use your own method to work on.
Dr. Shi, we have an online question.
Okay.
So can CEA be applied for a mixed-use neighborhood having area of 10 to 100 acres? Acres, probably like a small 2-3 blocks.
2-3 blocks. Yeah, that's possible. I mean, our best scale is from 10 buildings to around 300. We know people use as big as 30,000 buildings, but that would take a lot of time. Mixed use for sure, and we have mixed use options for each building, and you can define up to 3 use types.
Yeah, I think one more question.
Okay.
I have a question regarding something very basic that I think I didn't understand, which is why I don't need it, thank you. Which is why the location of the solar panel on the building affects the emissions. Like if it's.
Okay.
Yeah.
So if you apply the PV panels to everywhere on the building, that's the max yield can have, right? But you use, let's say, 100 units of PV panels and you produce 100 kilowatt hour electricity, for example. But if you only place PV panels on where there are more solar radiation, and then you have like 20 unit of PV panels and you generate 80 kilowatt hour, not 100, but like 80. But if you calculate the intensity, it would be 20 units of PV panels divided by 80, which is the carbon intensity. And the other case would be you have 100 unit of PV panels divided by 100 unit of electricity. So the ratio would be 4:1, right?
I understand the math, but I don't understand why, let's say I place a panel on a south facing side of a building versus on a roof.
Yeah.
Why would one emit more carbon, like negative carbon to the carbon emissions? Why would one have more than the other if they're both receiving?
Because the way you calculate emission is based on the amount of PV panels like you install, which is manufactured somewhere, right? That's embodied emissions.
Oh, I see.
And you divide it by the quantity of the yield.
Okay.
So if you place somewhere that's useless, and you're wasting that emissions on that, right? Yeah.
Thank you.
Welcome.
Yeah, I think there is one more question.
Yeah.
Can we have one more question?
Some thinking process in relation to the design of the building, in relation to the different technologies, if it's an office building, if it's a residential building, the building envelope, usually office buildings have the more glazing on the facade. And in relation also to the higher needs, cooling needs, or cooling loads in office buildings, in relation to residential.
So there's a very good question. We have a built-in database to solve these. So when we have a database, for example, like architect, the typical office building, what would be the cooling? A typical residential building would be the water use, the hot water use. So this is behind internal CEA. And the glaze also, like the same archetype will have data points showing, oh, this archetype of this building will have this more glazing on the building, or window to wall ratio will be 1. And the residential would be like typical windows, right? Windows to wall ratio will be 30%. So this is we use an archetypal mindset to work on.
So you're estimating PVs on the glazing?
There is an option you can opt out, like if you don't want to use PV on the window, and you can opt out only taking wall into consideration. Yeah. Thank you.
Hi, Shi. Hi, Zoe.
Yeah.
Thank you. Great stuff. And I want to maybe ask one question also for the benefit of the people who will try to or want to use CEA. I was part of the first workshop in Zurich of the CEA workshop with Amar and Martin back then. I sensed then that it's really contextualized on the LCA database that we use in order to produce meaningful and reliable results. So the problem we have in Israel is that we are heavily focused on operational energy. Like these carbon calculations are only just beginning, and we need to, sit or rely on a really reliable database. So what do you think about our context? How can we use CEA?
Yeah, so first, the model is, background story. I was helping out in Singapore back then when you had that workshop, but I was not in Zurich back then. So the model is universal. The problem is the database. And with built-in database in CEA, we have German database, Swiss database, and Singaporean database. And we also know in Netherlands, in Brazil, in China, some countries, Sweden, and they produce their own big database as a research team. But we don't have we're not collaborating with them, but we know that people can do that. And it's not a very difficult thing to do. And for Israel, I think there will be some 1 month of data preparation work if you want really to have a local data. But in the meantime, what we're trying to do is we always say we don't want to trust the absolute value of the simulation results when you compare different design scenarios, right? So as a quick application of the software in Israel, if you use the Singapore database, also to some extent.
That's great insight. Let's create that database. Thank you so much.
Yes.
Thanks.
Yeah. Thank you.
Thank you. Thank you, Dr. Shi.